Right, I'm going to share my screen. Good. Okay. So hopefully everyone can see. So I'll just bring up the chat window in case anyone messages. And yeah, okay. So yeah, so it's a pleasure to be talking to the Astronomy Society today. I think the last talk I gave was 2 years ago already, or 3 years ago. So as Claudia said, the topic of my actual research tends to be more about binary systems and pulsars and neutron stars. But today my talk is about a lot of things that I don't necessarily work on. So it's not necessarily my research that I'm presenting, but that of others. And yeah, and maybe, in the future talk, I might talk about Earth observations for tracking weeds and things like that, and how it connects to astronomy. But I'm still working on that quite extensively. So maybe next year. So the original version of the talk, actually, I prepared 2 or 3 years ago. So I've updated it a bit, but I purposely left out some of the more recent discoveries because otherwise the talk would have been too long, for instance. And I made some judgment calls about what is the decade. So there might be things that are a bit, the decade should be 2010 to 2020 roughly, but give or take a year or two. So I'm just curious to see in the chat, before we get started and get too far, I believe I have 8 major discoveries in there. So I'd just be interested to think what people believe might come up in terms of discoveries in there, just to see, what you might expect. So, if you get a chance, please just write in the chat what you think. Gravitational waves, black hole photo. Anything else? I think there's like 20, 30 odd people in here. Black hole image. Yep. Yeah, TRAPPIST. Okay, interesting. Yeah, exoplanets. Cool. Okay, well, I'll get started, and you'll see what I have, so you can try and make your sort of top 5 or something. Okay, so so by the way, the type of astrophysics I do is sort of at the boundary of observations and theory. And in terms of observations, I work across the entire spectrum. So when there's no pandemic, I actually tend to go maybe once a year or so to La Silla in Chile to observe. So the telescope I use is actually on the other side of the camera. You don't see it. It's called a New Technology Telescope. It's a 3.6 meter telescope. So we've been taking a lot of data there in the last couple of years. And that's the instrument I use. It's called UltraCam. It's at the end of the telescope. So it's mounted on what we call the NASMIT focal plane. So basically the telescope has got this primary mirror and the secondary mirror. So light comes in, reflects off the primary, then secondary, then it comes back at the bottom. And instead of putting an eyepiece or a camera there, actually there's a mirror that can flip and change direction, and then it can direct the light towards the sides. So it enables us to basically put it at the pivot point of the telescope, and therefore mount heavier instruments and whatnot. So yeah, and yeah, this is just a nice moonrise just before the sun got up when I went observing last time, and you can see also Jupiter just below. But some of the data also I take at Jodelbank, not during the Blue Dot Festival though, but when there's nothing going on. And I still use it extensively as well. But like I said, a lot of the discoveries mentioned here, actually, I've got nothing to do with them. But sometimes I do have connections. So the first one, I think, that was the most popular choice. Discovery of gravitational waves, ripples in space-time. So that's probably in my opinion, the most important discovery in astrophysics, potentially in the last 100 years. So gravitational waves had been predicted by Einstein. When the theory of general relativity came up. So for those of you who are, doing undergrads in physics, you'll probably eventually get to general relativity if you pick it in your third or fourth year. But you've seen already special relativity, space-time as 3 spatial dimensions and a 4th one, which is time, and they're all interlinked, and time and space are not really much different from each other, really. So, and what we learned from Einstein in 1905, from the special theory of relativity, is that time and space are actually concepts that can actually look different, right? Depending on the point of view we are. So depending on what we call the reference frame. So especially if you're moving at a certain velocity. So time can contract, can dilate rather, and space can contract. And with general relativity in 1915, then what Einstein discovered is basically that our universe is basically like a malleable fabric. And when you put mass somewhere, then it creates some sort of curvature in space-time. But you could also see it the other way around. So you could think of a distortion in space-time as basically creating mass somewhere or implying that there's mass. So in the actual discovery papers, because there were 4 papers, so it was called the month, like Mirabilis, which basically, the amazing month, because Einstein published 4 first author papers every single week of November in 1915. So it's pretty much like everyone's, dream. And he explained like the perastron advance of Mercury and different things like that, like bending. But then a year later, what's less known is that a year later in 2016, he published another paper where he was basically discussing the concept of gravitational waves. And then after that, people took up the concept and, evolved it. So what is gravitational waves? Well, basically, if you take masses in space and you accelerate them, so either linear acceleration or you accelerate them because they're in orbit around something, so due to the curvature, basically due to the centrifugal acceleration, there will be gravitational waves emitted. So if you take a binary system, for instance, because they orbit each other, they keep accelerating, and therefore they produce constant gravitational waves. And these waves are literally ripples in space-time that propagate outward. I'll just pause the video right here. So and just move back a little bit. So when they orbit, these waves, they carry energy with them. And as a result, the energy needs to come from somewhere as per conservation of energy. So the place it comes from is basically in the binding energy of the system, which means that the binding energy decreases over time as a result of gravitational wave emission. And so you can expect, therefore, the separation of the binary to decrease. And so this is what leads a binary system to eventually coalesce, to merge. For that to happen, though, the 2 stars or the 2 objects need to be quite massive, and they need to be quite close from one another. Otherwise, other types of effects might dominate, like tidal effects or things like that. But if you have like a binary black hole, for instance, and it's sufficiently small separation, then they might collide eventually. So when the collision happens, you have a huge burst of gravitational waves that's created. And then these waves, propagate when they encounter Earth. Literally space-time at Earth will dilate and contract. And as a result, we can, detect or hope to detect that. What's really difficult, though, is to, the actual detection of the signal. Because these gravitational waves, I see a question, so I'll address it as I speak. They propagate at the speed of light, but the distortion they create in space-time are something like a fraction of the width of a proton in terms of amplitude. And the gravitational waves, so for those who have done a bit of wave physics, you probably heard that electromagnetic waves, so just regular, light, is a dipole type of radiation. So you have a wave kind of like traveling like that or like that with some polarization. Whereas gravitational waves are quadrupolar radiation. So this means that it's not a wave like this that propagates, but if you imagine the wavefront that propagates, say, in the plane of the screen, like towards, inside towards the screen, then it means that it will make space shrink in one dimension, which is perpendicular to the propagation. So space might shrink this way. But then in the third dimension, the third axis, so up and down, space would dilate. So basically, if you had like test particles that were able to measure some position in space-time, as the gravitational wave passes, it would shrink like this, but elongate, and then it would do the opposite, half a cycle of the wave later. So you have like this sort of like breathing kind of motion like that as it propagates. And this is what we're trying to detect. So in order to do so, we basically use instruments such as LIGO. So LIGO is in fact two instruments, one located in Washington State in the US, and the other one is located in Louisiana. So they're several thousand kilometers away from each other. And each of them is basically a laser that's located in the facility that's been shined through this long tunnel up to the end there, a kilometer or two away, where there's a mirror, and it bounces back, comes back at the origin, and it does the same on the other arm. So the light, if we look at this little diagram, the light from the laser is actually split, using a mirror into, or a lens rather. It's split into two different propagating waves. And basically, it's a simple Michelson interferometer experiment, whereas part of the wave travels there and the other one travels at a perpendicular angle, and then they come back. And when they come back, there's a camera, and the camera will basically detect the interference pattern. So if each of the arms is exactly the same length, this means that the waves travel and then they come back exactly in sync. So you will see basically a bright spot on the camera or on the screen. And then if there's a small, change in distance, so if the change in distance was exactly half of the wavelength of light, then you would see a dark spot because the waves would come back out of sync. So you would have a maximum of the wave with a minimum, and that will interfere. So generally speaking, it's a more complex pattern that you see. So it's kind of like airy rings for those who are familiar with that. So concentric rings. And basically what's measured is the pattern evolving over time. And the evolution of the pattern over time basically just describes the relative motion of one arm compared to the other one. So with that, you can measure essentially the two dimensions of space, like sort of X and Y. And if there's a gravitational wave that comes in the Z direction or at some angle, then it would create this breathing pattern that would change the length. Now, it's obviously a very difficult experiment to do because even tumbleweed, rolling on the ground at the surface will actually create vibrations that can be detected by the interferometer. Similarly, if you have airplanes that fly in the sky, they can also detect these vibrations or even like the sort of gravitational field of these. So the lasers are extremely powerful and precise so that you can measure the interference pattern really well, but also the mirrors themselves, there's like a very complex system of pulleys and such so that they can isolate them as much as possible from vibration, like seismic vibration, for instance. So with all of that said, basically 14th of September 2015, so after something like a decade of working on this particular experiment and collecting data. There was an upgrade to the system to make it more sensitive, and then they finally detected gravitational waves. And this was from 2 black holes, each of them about 30 times the mass of the sun, that collided. And we can actually measure the distance. I can get back to that later, but basically the distance to these black holes is about 1.2 billion light years. And the stretch, right, that was measured at the detector was about 10 to the minus 19 meters, right? So it's something like 1/10,000th of a femtometer, right, which is the characteristic size of a proton. So really, really, really tiny signal. What you can hear now is the actual sound of the gravitational wave. So you can imagine it's a vibration, so of the interference pattern. So if you were to take that inference pattern and make it sound, this is basically what it would sound like. There are 2 variants, like there's one at a higher tone and one at a lower tone. So the real frequency is the one at the lower tone, but it's been also increased in frequency just to help sort of visualize. So the signal, so I'll just quiet it a little bit. So you basically have I'll just pause it. So you have the frequency of the signal as a function of time. So you can imagine you look at the mirror and then you try to measure the vibration on the mirror and the change in distance. So the variability in distance is basically displayed on the vertical axis. And on the running axis is how this changes over time. So what you can imagine is basically, so that's the color map that's at the background. And then on the, well, say foreground, you have like the actual waveform. So basically the waveform represents the amplitude of the signal as a function of time. So you basically have like nothing or noise. Eventually the gravitational wave passes. So you start having something that's regular. So that's what you see in the waveform that's right here. You start having a couple of oscillations. And then these oscillations increase in amplitude because basically that's the splash. Like these few regular ones at the start are basically when the black hole is about to form. So it's the two individual black holes that are starting to touch. And just before they touch and merge, like the amount of gravitational wave increases. So you have like a steep increase in amplitude of gravitational waves in the last couple of orbits. So you basically track something like 2 or 3 orbits of the final orbits. And then they merge, but as they merge, you have a blobby, probably peanut-shaped black hole for like a few instants. And therefore, like this still rotates, so you still have like oscillations. And then you have the largest amplitude. And once they're merged, basically then there should be what we call a ring down as it stabilizes, and then the black hole becomes a perfect sphere again. So from studying like the sort of precursor to the merger, the actual sort of merger phase and the ring down, there's also a lot of physics that can be understood from that. So you can also notice, right, the wave pattern as a certain frequency, and then the frequency increases, and it's basically just the binary, right, having a shorter and shorter orbit, and until eventually it's like just the one. So that's what the color scheme is. Basically, it's what we call a chirp signal. So basically you have like something at a more or less constant frequency, and then the frequency rises essentially, exponentially until it just disappears. So when they search for gravitational waves, there's a lot of noise, but basically what's done is searching for this characteristic chirp noise in data. So it's done with like special match filtering and other algorithms that are, specially designed to pick out that sort of signal. Another very exciting, so, some of these discoveries are kind of like multiple aspects. So there was also 17th of August, where we detected the very first double neutron star merger. So the first event was 2 black holes, and this one is the first time it was 2 neutron stars. And why it's relevant is because when black holes merge, the expectation is that there's not going to be any signature that's visible in terms of electromagnetic spectrum, right? Because the black holes, they they contain their mass, so unless there's matter around, there's nothing that should escape. So therefore, it's not really expected that it would produce a light signature. Whereas if you have a two neutron stars, or potentially as well a neutron star and a black hole, then you might expect some kind of a fireworks. And so that's what happened with these two neutron stars. And the firework that it produced turns out to be a short gamma ray burst. And these have been observed for something like 40 years now. And people didn't know for sure what short gamma ray bursts were until this observation. And then it just proved it, because basically the gamma ray burst was observed at exactly the same time as the gravitational wave in the same part of the sky. And so it's clear now that there's the association. So short gamma ray bursts are caused by double neutron star mergers. And then after that, the outcome is a black hole, most likely, and a bit of matter that's been scattered around from the merger. So this produced what's called a kilonova. So that's visible in the optical. So on the bottom diagram here, you have like the same chirp frequency from the merger. Then right next to it, you have two gamma ray satellites, so Fermi, and another one called Integral that observes slightly like harder gamma rays. And you can see that there's a spike that took place something like, within 2 seconds of the gravitational wave event. Then you can see on this diagram the celestial sphere, and the blue contour that's right there is basically the region where the gamma ray burst was detected. So it was not very well localized. But then LIGO also cannot localize, perfectly precisely where the waves come, because you have two detectors, right? And they're at different places on Earth and at different orientations. So you have the wave coming. So if you only had one detector, you could not tell, if the wave comes like this at the amplitude you measure, or if it comes at some angle, because there's basically some sort of cosine of the angle at which it comes compared to the normal, to the detector plane. If you have two instruments, right, and they're at different angles, then you can actually constrain much better the direction by combining the two. But it's not perfect. And in fact, people are working well, there's another instrument called Virgo. So Virgo is less sensitive. It's located in Italy. It's less sensitive than LIGO, but it didn't detect the gravitational waves. But given it didn't detect it, you can put limits that can actually also help rejecting portions of the sky. And in the coming years, there might be a new detector as well located in India, and maybe one also in Japan, and maybe eventually also even one in Australia. So when all of these work together, then we should be able to get like degree precision in the location of the waves. But for the minute, it's like thousands of square degrees. So when some such event takes place, we need to hustle and basically go with a bunch of telescopes and search if there's a counterpart. And so that's what people did, and then they got really lucky because they did find that kilonova. So basically that's the light in the optical at different wavelengths, and then basically they saw a huge increase of a source that was not visible before, and then it increased by a few magnitudes and then started decaying until basically not being visible anymore after a couple of weeks. Okay, so that's enough for the gravitational waves. There was a few questions. Maybe I can answer a few ones real quick. So how common do we think orbiting black holes are? Well, there's a lot that I would need to think a bit how many there might be in our galaxy. But the couple of black hole discoveries so far have been very puzzling, because they're more like tens of solar mass black holes. And those, they should be pretty rare, because most stars that explode would be more like, maybe 10 times the mass of the sun. So to form a black hole that is 30 times the mass of the sun, you need a star that initially is probably 100 or 200 times the mass of the sun, but then they're very rare. And it's not even clear that they would still even form a black hole that's that massive. So to have like these sort of very massive black holes, you need to tune in the evolution very well, or you need maybe the black hole to accrete a lot of mass or to combine with another black hole prior. So there's quite a lot of challenges actually with these discoveries. Now, LIGO, when it starts observing again soon, we expect that we will detect a double black hole probably every week, if not a bit more often than that. And so that's within the sort of portion of the universe that it's sensitive. Neutron stars are a bit more rare or more difficult, I would say, to detect for LIGO. So they're more rare than double black holes, but the events are less, bright for gravitational wave detectors. So they're less bright. So we expect maybe something like once a month or so. So yeah, and then there's tons of science you can do, like these signals might be redshifted, or so we can probably use black holes as standard candles, a bit like we use type 1a supernova, and then map like the scale of the universe as well. So these are all things that can be done. Then you can compare like the time you get the gravitational waves and the time you get optical signal, and then you can try to put constraints on the speed of light, for instance, because both should be traveling at the same speed. So there's all kinds of exciting science. So I'll just save, some of the details for the end in case there are questions, just so I can cover the other slides. Okay, so TRAPPIST number 1 is the second one in my list. So I think Claudia had flagged that one. So it's really redefining our concept of planetary systems. So I'll just start the animation. So this is the planetary orrery. So basically, it shows. Well, at the time this video was made by G. Abramson, it showed all known exoplanet systems or extrasolar systems. So you have like to scale basically the size of the exoplanet, and you have like a color that gives the temperature that's expected for that planet, and then you see the orbit. So the size of the planet compared to the orbit might not be to scale, but the size of the orbits compared to one another is. So like a few years back, there was already like 3,600. I think we're probably closer to 4,000 these days. Something people don't know is that the first exoplanet was actually found around a pulsar. So I like bragging about it because I do study pulsars. So with pulsars, we can measure the rotation really well. And so if it's in a binary system, you see the Doppler effect from the orbital motion. And they're so accurate that we can actually measure orbital velocities for pulsars that are fractions of millimeters per second. So all you need is, basically a sort of like exomoon or something like that around a pulsar, and in principle, you can detect its presence. So in the early 90s, that's basically what happened. We had found already a bunch of pulsars that have a white dwarf or another star as a companion, but then the signature of a very lightweight object was revealed by one of the observations. And we're talking about like, Earth mass kind of objects and Jupiter mass type of objects. Actually, that one system had 2 at the time that was discovered. And they were so low mass that there was no way that even if you change essentially the angle at which you see the system, that it could, because you only see the radial velocity, but there was just no way you could make it massive enough to, be a star. So it had to be a planet. And the question was how they form, right? So because the pulsar formed in a supernova explosion. So if there's a nearby planet, you would expect it might get disrupted or something like that. So one of the leading theories is that these planets are formed by accretion from the remnant of the supernova, rather than existing in the first place. So the Kepler mission has been really important. So it's a satellite that's pointed like in one direction of the sky for something like a couple years. And it's found through the transit method about a third of the known exoplanets. So the transit method is quite simple. If you have like a big planet that orbits close enough from a star, and you're observing it quite close to the orbital plane, then when the planet passes in front, you'll have a dark spot in front of the star. So you'll have a little dip in the light, and that's what we call the transit method. And it's the most successful because we can measure the flux of stars really accurately. And for instance, Kepler, depending on the brightness of the whole star, Kepler can detect changes in light that are something like 1 part in 10,000 to 1 part in 50,000 quite easily. So this means that, you know, objects like Jupiter size that are in orbit of a couple days, they are easily detectable. Then if you put the planet further away, like at Jupiter type of distance from the sun, then the dip in light is much smaller. So there's some sort of selection effects, but still, we were surprised to find that basically there's so many exoplanets that are that close to the host star. There's also the direct imaging method, which is quite neat, but a lot more challenging. So what you need to do is you need to mask the actual flux from the star because it's too bright and the planets are very faint. So the contrast you need is like huge. So these days, instruments are able to have a coronagraph that are able to put like a little tiny, like hairpin, you know, right at the position of the star so that you can see what's really close to it. And this discovery of that, you know, first direct imaging was made by people in Canada. One of my colleagues at the time when I was at the University of Toronto was one of the co-discoverer of this 4-planet system. So you can see 1, 2, 3, and there's a 4th one out there. And so you can see the time lapse. So it's really impressive. But TRAPPIST is more has to do with the transit method. So this is the light curve from TRAPPIST-1. TRAPPIST is a small telescope that's located in La Silla. Actually, it was on the image I showed with me, you know, at the start of the talk. And it's a small sort of 1 meter or 2 meter telescope out there that's operated by a Swiss, by the Swiss scientists, but it's an international team. And one of the stars showed dips, so clearly an exoplanet. But then the dips were all over the place if you look here. And then actually, if you start labeling them and looking if there's anything that repeats, then what you realize is that there's like 1, 2, 3, 4, 5, 6, 7 planets orbiting around that star. So it creates like a myriad of, you know, dips. So it's really amazing. But what's even more amazing is the fact that 4 of these planets are located right in the zone. So you have like the comparison to the solar system here. So you have like Mercury, Venus, Earth, Mars. And if you zoom in, like that tiny fraction of the solar system, that's about maybe a quarter of the orbit of Mercury, and you expand it, that's basically the size of that planetary system. And it's only, you know, something like 3 times the size of, you know, the Jovian orbits, you know, the Jovian moons around Jupiter, so Callisto, Ganymede, and Europa, Io. But the star that's there is because it's a dwarf star. So it's something, I forgot the exact number, but something like a 0.3 solar mass star or something like that. So it's much less luminous. But then when you calculate, it turns out that 4 of the exoplanets are in the range where the radiation is large enough for the star so that water should be liquid. And so that's really exciting because, you know, if there's life out there, then it could be located on 4 different planets. So here you can see some of the, you know, the numbers. And the inner one is at 1.5 day orbital period, and the furthest one is 20 days. And that compares to Mercury, which is something like 87 days. And the size of planets varies between about 1 times the Earth radius to, for the smallest one, which is this one, the further out one, 0.76, so about 3/4 of the mass of the size of the Earth. And then you have like an approximate density for these planets. So 4 of them could have liquid water, so it's really exciting. And there might be a lot of these systems out there. Okay, so third discovery, the moon is wet. So Now, it's something that's always puzzled us, right? What is out there on the moon? Before we could actually go there with spaceships, and then, okay, when Apollo went, like, it was clear that the moon surface is dusty and it's rocks and everything, and it's not quite clear that there would be water. And then various missions with flybys and satellites had maybe said that there could perhaps be water, but there was nothing quite clear about it. And that's until the ELECTROS mission, which is basically a satellite that went and mapped and did various measurements around the moon. But the mission was special because it had a probe that detached from the satellite and plunged right onto the moon. And the idea was that it was part of the NASA mission, which were like faster, cheaper mottos. So they could not afford sending a robot on the moon and take samples, and everything was too expensive, basically. So the idea they had was, let's just shoot something on the moon's surface, and let's just get a big splash, right, of soil to come up. And then let's use a spectrometer and take imaging of that splash. And so if there's any water, then we'll see, water vapor, basically, once it's pulverized and comes up. So that was basically the idea, to get an idea of the moon composition, like below the dust layer of the and then they sent that mission to go right into a crater that's near the pole of the moon, because obviously if you're near the equator on the moon, then half of the time you'll be directly exposed to the sunlight, and then we know that that ice would basically turn into gas. So there cannot be water like near the equator. It has to be near the poles, deep in a crater where it's always dark. So you can see this image. It's a zoom in of the pole, and you can see that little white dot there, right here, and then expanded more. So that's the plume, basically, from the impact. And then from the spectral analysis, they found that about 5% of the content of what came out was ice, was water ice, not any type of ice, but water ice. So it's quite exciting. So it means, we heard, like, especially recently, like ESA and then the Chinese and maybe even the Americans want to return back to the moon. So if we set up like some sort of a lunar base, it would be really good if we could source water locally, because, obviously that's what astronauts need long term in order to survive. And also then you can also split water into hydrogen and oxygen, so you can breathe, so you can not only water to drink, but also things for breathing, and also then the hydrogen can also be used to make propellant to return back. Then next one, dirty snowball. So you have an image of the Hale-Bopp comet that came in 1998. I saw it as a teenager back then. It's probably one of the best comets, to be honest, like from the last 50 years. It was amazing. And comets, you probably all know, they're big boulders of ice and dust. They're a couple of kilometers across, and unlike the planets, these have very eccentric orbits around the sun. So comets like Halley's comet, they go as far as roughly Jupiter/Saturn orbits, or just a bit beyond, maybe Uranus, and then they come back near the sun. So Halley has a 76-year orbit. But then some comets come from much, much further. So Hyakutake, for instance, in 1996, came at the Periastron. It's got a 17,000 year orbit. So it goes really, really far. So it goes into a region that we call the Oort cloud, which is what we believe is a big reservoir of like boulders that are like comets, and sometimes gravitational disturbances makes one plunge into the solar system, basically, and we see it. So they're really important because we believe that the material they're made of are basically the leftovers from the formation of our solar system that's been unchanged, right? There's no tectonic plates, there's no humans, there's no atmosphere. Sorry, I got back on my side. Please turn off your microphone if you can. Thanks. Yeah, so there's nothing. So it's basically pristine material from the solar system. And so back in 1986, when Halley came last time, there was a probe, a spacecraft called Giotto that went near Halley and took this picture of the actual comet, and you can see the outgassing. So it was amazing. It was all over the news and in every newspaper. But then not too long ago, in 2015, there was a 10-year mission. So it took 10 years to go and catch up with a comet that was coming in the inner part of the solar system, so-called Churyumov-Gerasimenko. And that comet, then the probe started orbiting around for about 2-year mission. So prior to the perihelion, and then after when it went over. So back then in 2015, it had just started coming close to the sun, so you could see the outgassing from the surface. But I mean, this image is amazing because you can see the comet has like this sort of peanut shape. Then you can see the surface being very irregular, full of dust. So it's really amazing. And then, you can see like boulders on the surface. It's just astonishing. But the other thing about the mission was that there was a little probe, a little lander called Philae. And so it's 100 kilograms, so basically size of a large human, that would go and land on the surface, and then had a little robotic arm and was supposed to take samples from the surface and analyze them. Sadly, there were some issues. So when it landed, it actually bounced off the surface because the sort of harpoon that was supposed to be used to, remember, this object is only 2.5 kilometers. So the gravitational field is really weak. So, a human could potentially, going on the surface, could probably jump and almost like get into orbit. So when the probe came down, there was nothing to slow it down, basically. And then they didn't want to use thrusters and everything, would have made it more expensive and whatnot. So it basically bounced off the surface. But the idea was that it was supposed to, hold onto the surface, and it didn't work. So it made a bounce and went something like 1 kilometer above the surface on the first bounce, and then fell back on the surface and then made another bounce, and then eventually it managed to fall and stay there. But then it didn't fall in the perfect orientation, so some of the measurements that were supposed to be made didn't quite work. But overall, the mission was a success. Like there were many instruments on Rosetta, and they could take measurements of the composition of the outgassing tail of the comet at different times. One of the major discoveries was that the water that they found in the gas and from like the surface, you can look at the abundance of water versus heavy water that's made of deuterium, but also you can do the same for oxygen, right? So oxygen has a few isotopes. So oxygen 16 is the most abundant, but there's other isotopes of oxygen, and you can look at those, and then you can compare the abundance to, for instance, the abundance of what we believe is the original abundance of water and oxygen on Earth, especially for water. Because one of the primary theories for why we have oceans and so much water on Earth is that early in the solar system, once the Earth was formed, there was a heavy bombardment of comets on Earth that basically brought the water. And it turns out that the isotopic abundance of the comet is different from that of the comet, of this comet. So it sort of hints that maybe comets were not responsible for bringing water on Earth, and maybe it was just there in the first place. But ideally, we would have other comets to compare with, because maybe this one is just a bit special. Okay, number 5, New Horizons. So that one maybe you've forgotten, but it's a big one. So it's a space probe, went towards Pluto. So it was the very first space probe to make to go nearby Pluto. And actually, it was too expensive and complex to actually, well, too expensive pretty much to get the probe to stop at Pluto and orbit around it. So it just did a flyby over Pluto. But still, it was enough to do a lot of studies. So Pluto, you know, growing up, and there was one moon around Pluto, but actually with Hubble and other telescope, we ended up concluding that Pluto has 5 moons. That's pretty amazing, given it's the smallest planet in the solar system. And Charon, actually the primary moon, is about something like half the size of Pluto itself. So it's almost more like a mini planetary system than, you know, a planet with moons, if it makes sense. So when studied the geology and everything on Pluto, so Pluto is covered by a crust of icy hydrocarbons at, you know, that distance. So if it was closer, it would probably be more rocky, but then at this distance, it's got like frozen gases basically. But it still has like this tiny atmosphere, so you can see the great picture. And so we learned quite a bit, you know, on Pluto. I won't expand on the, you know, all the details of the discoveries, but after passing Pluto, they, you know, there was some fuel left on the engine, basically on the thrusters, and so they directed the course of New Horizon just ever so slightly, so that in the long run it could actually intercept another object. So we know that our solar system is littered with, you know, these comets and asteroids all over the place. So there's the Kuiper belt that's somewhere between Neptune and Pluto, which is basically a big kind of asteroid belt / comets, and Pluto is most likely one of the major objects really of that belt. But further out, when you go much further, there's the Oort cloud, which is what I was talking about for comet reservoir. And so it's a lot further. But then there was there are objects that we see. We can see them with like telescopes with like Hubble. They're very faint, but they're like big, you know, giant asteroids or the likes that are located on the outer solar system. So Senna, which was one of the biggest such pseudo planet that was known, like that's the orbit compared to that of Pluto in pink. So now they managed to actually change the trajectory to intercept with one of these trans-Neptunian objects. So it's called 2014 MU69. Then they named it Ultima Thule, and then they renamed it Arrokoth. So that latter word actually is an Algonquian word, so a Native American word, and it means sky. So that's the official International Astronomical Union name. So it passed that object on 1st of January 2019. So it took an extra basically 5 years after flying over Pluto to reach it. And it went past this minor planet. So here you can see, I'll just turn down the volume. You can see an image. So it's basically a time lapse of the from the camera on board the New Horizon. So it's basically located 40 times further than the sun than Earth. So 44 astronomical units. And then you can see, now you can start seeing the rotation and actually the irregular shape of Arrokoth. And so it's kind of like a peanut again. So most likely it's 2 objects that formed and collided and ended up glued on top of each other. And then this is as the probe like went further away and could just see the small limb, you know, the crescent basically from being illuminated by the sun. So it's the furthest object we've ever visited. And I believe they're trying to get New Horizon to keep going and hopefully go past another object one day. Right, number 6. Our jewel of the solar system, Saturn. So Cassini-Huygens was launched in 1997. It reached Saturn in 2004, and for something like the better part of 13 years, observed Saturn from all angles and also its moons. So it studies the ring, moons, the magnetism of Saturn, the space weather around Saturn, and there's some really exciting discoveries it's made. One is about Titan. So Huygens was a little probe attached to Cassini, and it was ejected from the probe when it got to Saturn, and Huygens basically just went into the atmosphere, slowed down with parachutes, landed on the surface, and took some images from the ground there and some measurements, and then relayed to the probe to get to us. So it's the moon that has the densest atmosphere in the solar system. So there's a couple of moons that are known, and this one has a really thick atmosphere, which is made mostly of nitrogen and hydrocarbons. So you could almost imagine it as perhaps a pre-Earth, type of atmosphere, because originally the Earth's atmosphere was probably rich in hydrocarbons and nitrogen. And it's got lakes, it's got like liquids on the surface, except that it's liquid hydrocarbon. So you can think of like, liquefied methane and things like that. So it landed in 2005. So just at the start of the Cassini mission. So that's why I'm cheating a bit with the decade, because in that case, the mission was overlapping between the two. So the atmosphere is quite dry, but there are clouds in the atmosphere, so we cannot see the surface directly. So people were really curious to see what the atmosphere looks like. And basically it looks like a desert. It's got like rocks and pebbles all over the place. The atmosphere is a bit wet, but only 50% humidity, but it's not water humidity. So it's methane relative humidity. So it's quite strange. And the surface has got this sort of like little crust. So there's like solid stuff, but on top there's this sort of dust, which is kind of like crusty. So you can imagine it as a bit of like creme brulee or something like that. Yeah. Also, sometimes there are showers on the surface. So basically the methane evaporates, forms clouds, and then it rains down. So it's really, really strange. And it's probably a really cool place, one day maybe to, even send like humans to explore there and try to maybe turn, some of these into, an habitable place. Some of Saturn's moon are weird. Like this one has got like this little tutu around the equator. It's called Pan. And it's basically believed that the moon was formed in two stages, probably like something formed and then something else collided into it. And then there was a debris field around, and then it fell back onto the surface and formed that little ring. So you can see an animation of the flyby from Cassini, seeing it on different angles. So it's really strange type of object. Then you also have like this weird cloud formation near the pole of Saturn. It's got like a very pretty much perfect hexagon shape. So people were, then you have like all these conspiracy theorists and whatnot who got wild, it's gone wild about it. But it turns out that it can be explained with fluid mechanics. So people started working on the problem. And it turns out if you have viscosity and the viscosity changes in altitude, then as you have shear forces from the winds, it will actually start taking patterns. They're basically sort of like resonances. And you can actually start forming like geometrical shapes rather than, just roundish shapes. So that's how you get this hexagon, basically. So it's from the differential speed at different heights. Then, the rings showed like this little hump there. So it's probably a moon that's forming into the belt. So the belt is multiple small objects, but sometimes there are more stable regions, and they can actually form small moons, we believe. So we call them the shepherd moons. Then Enceladus, one of another moon of Saturn. Actually, this one is like crusty. We believe there's an ocean underneath, and there are geysers. So you can actually study like the composition of what's ejected, and it's actually rich in water vapor, hydrocarbons. So the sort of stuff that could, potentially harbor life. So there's an idea for NASA to go and like drill down. Okay, finally, real quick, fast radio bursts. So that's closer to what I study. Actually, I study some of them, and other colleagues at JBCA do. So they're these one-off really bright events. So a radio flash that you detect with your radio telescope. So here it's Parkes, because the first couple ones had been discovered with Parkes in Australia, and they last a few milliseconds. So it's like this little bleep, and then it just disappears. And you can tell it comes from very far, because the bleep you see comes with a delay depending on the radio frequency you observe. And this sort of delay is caused by the propagation in the interstellar medium. So it's something we see all the time with pulsar, and basically it enables us to tell the distance. And so a burst like this one came from like billions of light years away. So it's outside our galaxy. We just didn't know what it was, and still don't quite know. But then for a while, the telescope also detected like some other bursts. And then, people were like, oh, are they real? Are they really, from outer space and whatnot? And then they actually found that some of the bursts tended to be clustered around noon every day. So it sounded a bit fishy because, why would bursts come around noon and not like just, uniformly? Because, if they're interstellar or extragalactic, even they should come from all directions and at just any time. Turns out some of the bursts were microwave signal. So the telescope, there's another little building where there's a kitchen. And when the telescope tilts down, sometimes it can actually pick out some of the signal from the microwave. And the microwave had to be tuned like just to the right setting. And even though the microwave should have been in a Faraday cage, when people would open it, like to get their meal because they weren't patient and the microwave had not finished, then they could get a burst. So it was only, occasional, and it took like 2 or 3 years for people to figure out. So when it happened, us at Jodl Bank, we went in the field, we took the microwave, took it in the field, and then tried to create like these fake bursts that we call peritons. However, fast radio bursts are real, so some are not microwave signals, so they come from really, really far away. And we still don't know what they are. They could be mini black holes exploding. There's all kinds of weird theories, black hole merging, super magnetized pulsars that we call magnetars, perhaps, or some giant pulses from pulsars. So there's a lot of development that happens with fast radio bursts. You might even have had a talk recently, or will do, or if you want to learn more, there's like half a dozen people who study them, so they can talk to you about that for over an hour. So I'll just stop here because I know I'm kind of out of time and there might be some questions. Yeah.
Thank you. Thank you so much. There's some questions in the chat, and maybe if people want to ask some other questions, they can unmute or they can put them in chat.
So don't be shy, please unmute and ask or write in the chat. So by the way, the one discovery I didn't include and I could potentially have done, right, is that recent one on Venus, right, about the phosphorine on Venus, like this, special molecule that's most likely associated with life, although it's quite controversial. So that's also why I didn't, there could be a full talk about it. And there are people like Anita Richard who were involved with the discovery also at here at JBCA. So they can give a full talk on that. Any question?
I have a question.
Yeah.
Yeah, well, first of all, thank you very much for the talk. It was just a very quick question. So about the last point you talked about, so the quick radio burst. If apparently it was because of the microwave that was in a near building, how do you explain the delay that apparently implied that burst came from billions of light years away?
Yeah, that's a good question. So I'll just get back to that slide actually. So so this is like this one, for instance, is like a real delay that's interstellar. So the delay that's on interstellar, you can work out from more or less like first principle physics. Basically, it has to do with the groove velocity in ionized medium. So what you can derive, like it's in Jackson or any ENM like book, it's basically the delay is proportional to 1 over the frequency. So it has to have a very specific shape. Now these bursts, like we were a bit suspicious because they were like, they were very bright at some kind of narrow range of frequency and then had a bit of a tail, but it was a bit, usually the bursts we expect, they're probably broadband, so they should be, not necessarily constant, they should have some sort of spectrum, but it might look more like a power law or something like that. So that was a bit of a giveaway that something might be weird. But the other thing is that the interval that they were measured was also fairly narrow. So it was, there was some uncertainty about the exact slope, so it's consistent with being like 1 over frequency square, but it could have been something else. And then, as it turns out, also only one brand or one manufacturer of microwaves seemed to produce that type of signal. So it's actually not necessarily the brand of the microwave, but inside there's a magnetron, as it's called, like so the piece of magnet, that heats up the food. It's basically some sort of electromagnet, basically, that's amplifying, that's basically beaming microwaves. And that particular one, it seems that when you cut the current off, there's some sort of like residual ringing in it due to the capacitance, the residual capacitance and inductance. And it basically naturally creates like this sort of like sloping signal that just so happens to coincide with that from the interstellar medium. So that was very unsettling.
Very interesting. Thank you.
I think we have a question in the chat.
Yep. Yeah, have we witnessed a 3-body system emitting gravitational waves? Are these systems even possible? No, we haven't yet, but they're very possible. I mean, there's nothing that exclude the possibility for, say, 2 black holes or 3 black holes to be orbiting each other, or 2 black holes and a neutron star or something else. It's just quite a bit less likely, obviously, because unless they are getting together after they are formed, they need to survive, say, one, if you have a black hole with something else, it needs to survive one supernova explosion. So it's quite likely that the system is disrupted. Now, if it's not disrupted, if the other object is a black hole, then it's 2 supernova that you need to survive. And so, that sort of process can, becomes less and less likely for everything to stay together. Also, a bit of an argument against, say, 3 black holes together is the fact that the stars need to be massive, right? And so typically, if you have one black hole that forms, then the other star had to be massive enough to also be a black hole. And then it would mean the third one would also need to be massive enough to become a black hole. And so there's a lot of processes in the stellar evolution, for instance, that could be such that even though the third one could originally form a black hole, maybe by the end of the day, it's not really happening. But in theory, there's nothing that prevents it. So maybe one day we'll see it. However, the event we would see, right, would still be a merger of probably 2 objects, right? So it would likely not be 3 black holes or 3 objects like merging at the same time. Because in terms of dynamical stability, typically what you have is like 2 objects that orbit each other with a shorter orbit, right? Quite compact. And then you have the third one that's a bit further out and kind of orbits around like the 2 of them that it sees almost like as one body. So that's the typical stability of systems, is more like hierarchical like that, rather than like, 3 object kind of equidistant that, just spin around. Yep. Anything else? Yeah, so as far you would need, so the question is, did we manage to reproduce these FRB signals? Yeah, so the fake FRBs, we call them peritons. They basically have a frequency drift in time, and not always exactly like this sort of 1 over frequency square, but it can be a bit different. But because the range that they produce light for is limited, it might overlap with. As far as I can tell, yes, they did. I was busy at the time, so I could not do it myself, but it was basically Emeritus Professor Ralph Spencer, and there was a couple of other people who went in the field and plugged in the microwave. But as far as I can tell, they did reproduce it. Yeah. So someone like Ralph Spencer would be a good person to talk to about that.
Hi, Professor. I've got a question. If possible. If you had to give this talk again in like another 10 years, what things would you like to include? Like what things would you like to see solved or found in the next 10 years or so?
Yeah. So there's the thing about Venus, right? That just came out in the like late summer or autumn. I think that's massively exciting. And there's been a bit of controversy about like maybe being not quite, a significant signal and everything. And I would need to even like dig in like quite substantially to form an opinion, because I think like some people still don't believe it and some do. And I think there was a 2 quick papers afterwards that contradicted it, but then the original people also went back and they said, no, actually it's still there, like maybe not quite as significant, blah, blah. So I think in a couple years, it would be, especially if a probe could go and measure it, like that would be massively exciting. So I think that's one thing. Then kind of connected to, the life out there, right? Because the thing about the phosphine signal is that it's something that's not necessarily produced naturally. So it has to involve some sort of like biotic, kind of process. The thing that's connected to life would be to detect actual kind of alien signals, right? And that, a couple of years back, or I don't know, growing up, I was kind of like, oh, that'd be really cool. But, it really sounded like proper science fiction. And I'm not sure what most of you might think, but I really believe that it's no longer pure science fiction and that we could achieve it for real. So the SETI project and the likes, I've searched for it. And there was a Schuster colloquium last year by Andrew Simeon, who's the director of the Breakthrough Listen initiative. And it's, they're searching for these signals, just like SETI has done, but now they have many more telescopes, better technology and whatnot to do so. But then the major breakthrough, so they might detect something if they get lucky, but I think the major breakthrough will come with the square kilometer array, because, especially phase 1 might be a bit more of a stretch, but you never know. But phase 2 of square kilometer array, so we're talking maybe 20 years at most from now, it will have like so much sensitivity that you could detect a sort of human type airport radar on a nearby planet, right? We're talking within like something like 30 light years horizon or thereabout. So this means, and that's been the problem of SETI searches for so far, because, it's always detection more or less of people would intend to communicate with us. And then you can imagine, unless say humanity would decide to beam something outward like continuously, but if you just do it every so often, it's quite unlikely you're going to be detected, let alone like, because it could come from anywhere in space. But if we can spy on people, right, if we just detect the leakage of the artificial communications they're producing, then I believe you're becoming like, hundreds or thousands of times more likely to detect a signal, because then people don't intend, but it's just from technology. And so with the SK being sensitive enough in something like 20 years or, then, well, who knows? But, if there are like sort of intelligent or technological societies out there that use radio waves, then we could potentially detect it. So I think, and that would be, mind blowing. So who knows? That could be within 10 years, maybe 20 years. And then maybe in 20 years, we'll be like, oh, okay, there's none. But then that could mean there's none overall, but that could mean also there's none like within, sort of 30 or 50 light years. But yeah, so I think that's another one. Then you might have heard in the news just like a week or two ago, potential detection of gravitational waves, but using pulsars. That one is really exciting because that's what I work on. So basically, just like LIGO, tries to detect gravitational waves with the interferometer principle, we can use the pulsar signal to essentially triangulate our position in the galaxy. It's just exactly the same principle of interferometer, except that we don't need to shine a laser because we have like a reference clock to tell us our Doppler shift compared to that source. So then if you have like enough of them in all directions, you can basically get a pretty good handle on how you're moving compared to them. And the thing is that those gravitational waves, they're not the same as LIGO detects. They're like nanohertz gravitational waves instead of being like subhertz gravitational waves or millihertz or hertz. And so these gravitational waves, much longer frequency, we're talking about wavelengths of light years, basically. They're gravitational waves that are basically the frequency of the wave for merging objects is related to the orbital period, basically, right? So if you have two neutron stars that merge, I mean, you can do like a lot of the gravitational wave physics with back of the envelope, like sort of A-level physics. So the orbital period of two, neutron stars that touch, I think it was even in one of the problems of like third year general tests a couple years back. Actually, it's a problem I think I put together. Anyway, so if you have two neutron stars, right, 10 kilometers in radius, and you make them orbit each other, like just touching, the orbital period would be about a second or so. And so that's those frequencies. But then if you look at supermassive black holes in the center of galaxies, then the orbital period just before they merge is more like nanohertz. So basically kind of year timescale. So with pulsars, we would be able to detect supermassive black holes colliding. And then that tells us a lot more about galaxy evolution. And it's a new revolution. Yeah. And the other thing is eventually we could also detect gravitational waves from the inflation period of the universe, which also is complete mystery and might be new physics. So I think that, will be very exciting. And there's a tentative signal that's just been detected. I don't have any more information, and also those I know cannot tell me more. But it's getting there. So that's also very exciting.
Brilliant. Thank you very much.
Yeah. So there's questions about philosophy or being fun. I mean, obviously, I hope I look like I'm excited about what I'm talking about. So for Eric, it's exciting to be an astrophysicist. It's always like research is just exciting in physics in general. It's never the same, but also astrophysics, it's just like, and also in terms of philosophy, right? It's the same, thinking about discovering aliens or the concept of space-time. It's just mind-blowing. So, thinking about all these issues, I mean, I could not single out like something, easily, but just black holes or neutron stars are just mind-blowing, right? Just thinking about their densities and the fact that, if you have a rotating black hole and you send a probe around it, it might actually, orbit a couple times and then be ejected and come back exactly in the same direction instead of coming back sort of like from the other side, because of like, the geodesics, like the lines of space-time for orbits and around black holes, where you can have a reversal of direction. Basically, it's just, it's just completely mind-blowing. So I try not to always think about it too much, otherwise I would just not get work done. But yeah. Anything else?